Hi, this is Cross.Enabla, and in today's video, we're going to be covering over section 13.4, triple integrals in Cartesian coordinates. So unlike in our past two videos covering over, well, actually our past three videos covering over double integrals, we're going to be consolidating everything into the Cartesian coordinates for both rectangular and non-rectangular prism regions and rectangular prism regions. It'll all be generalized because I feel like the information is relatively the same, right? And before we even start off, we should just probably look back at our previous types of integration and understand like how do we get here, right? So we get an area from taking an integral of a single variable function. We get a volume from taking the double integral over a region, f of x, y, in the xy plane. But we can also say that we have a triple integral measuring 4D space under a hyper surface, right, above the xyz hyperplane, or measures a signed volume given a density function. And we'll actually cover the latter example in section 13.6 when we cover over center of mass and density. You may have seen that already in physics, but we can reiterate that again. And we'll just show like the quick reasoning for that. We can't really, as humans, we can't really perceive the fourth dimension. And we're not talking about the fourth dimension being time. That's like a technicality, right? We're talking more about the fourth dimension of space, right? We are only processing 3 dimensions at once, right? So fourth dimension is imperceivable to us, but we can still graph under these three-dimensional spaces, and we'll actually show this on Desmos like we have been doing in these past couple of videos. But going with the latter example, we can actually talk about this, right? So if we know that density equals mass over volume, we can do density times volume equals mass. And then if you integrate this to get your density function in terms of x, y, and z, dv, you get your mass, right? That's just the way you would figure it out, right? And we can illustrate that in future videos as well, right? Example 1, this is really straightforward. If you want to pause the video and jump right into it, feel free to do so. And yeah, let's just jump right into it. This is, again, one of the more straightforward problems. We're not actually going to solve it for this one, just write out the iterated integral, right? And normally, I like to just write out dz, dy, dx as my order of integration. That's just the way I prefer it. Now, one thing I would like to mention before we even start this problem is that there are technically 6 different ways that you can order a triple integral. And I can actually just show that real quick. So we have dz, dx, dy, dz, dx, dy, dx, dz, dx, dy, dz, and dx, dz, dy. And that's just because we have three objects that we can permutate around. However, so often that's just 3 factorial, right? But there's always going to be an easier way to solve a triple integral. There's always going to be an easier way to solve the double integral, right? Whether that be in polar or in rectangular. And in triple integrals, you can do spherical or cylindrical or Cartesian. It really depends, right? And in the next couple of videos, we'll actually be covering over these types of examples as well, right? But jumping back into our actual problem, it's just a standard triple integral that we're working on. That would be 2, 5, 0, 1, y plus z plus 1, dz, dy, dx. And that is our solution. Perfect. Now for example 2, we're actually going to evaluate the triple integral. And you can actually look right here and you can see that we have all of these different planes crossing and intersecting with each other. And the cool thing about this is that we can actually illustrate this. This is kind of a low resolution image, but what we can see from here is our 3 coordinate planes, our x, y, and z, or at least an attempt to visualize that, right, on a 2D surface, right? And we can see right here, this rectangular or this triangular prism, in fact, is oftentimes what these shapes will look like are triangular prisms if it's given in this form, right? is actually going to give us our total volume, right? Technically, in this problem, we're given a density function and we're supposed to figure out the volume or the solution to this, right? I think what we can do with this is not too terrible for you, the viewer, or the problem solver in this case. And we'll actually show how to figure out the order of integration using Desmos or other forms of problem solving later on in this section, right? But yeah, let's just jump right into it. So we're integrating with respect to x first. So we would have to flip the order. So we'd have to take the antiderivative of that, which is antiderivative of sine is negative cosine. So then it would be negative cosine of x plus y plus, see, actually let's write this in red. I feel like red pops out to me more. We have to evaluate it from 0 to y. And we get this, we get negative cosine of 2y plus z, because we replaced the x with the y, minus negative cosine of y plus z plus. And then now we have our new double integral we can operate with. So we have from 0 to z and from 0 to pi over 2 to get cosine of y plus z minus cosine of 2y plus z dy dz. Perfect. Now again, we just have to take the antiderivative of this, which will get to be sine of y plus z minus 1/2. Oh, sorry, this should be plus. Wait, let me double check. This becomes a plus here. Oh, no, I did this right, yeah. It's going to be minus 1/2 sine of, minus 1/2 sine of 2y plus z. Let's just double check from my notes to make sure. Yeah, perfect. Okay, yeah, so I did that right. Okay. Yeah, because the antiderivative of negative sine will get you negative cosine. Yeah, perfect. Okay. Whew, even I have to remember all these little rules. Evaluating this, we get sine of 2z minus 1/2 sine of 3z minus sine of z minus 1/2 sine of z. So it's going to become 1/2 sine z. And then we have this as our new expression. Remember this all the way down here, 0 to pi over 2. And then we have, let's actually just copy this all over. I have to be a little bit cheeky with the actual dimensions right here. There you go. dc. And then this is just one last piece of integration, which we're going to get to be negative 1/2 cos 2z, negative 1/6, positive 1/6 actually, sine of 3z, and then, sorry. Oh my gosh, what is happening to me today? This past couple of videos have not been good. It's okay though. Cosine of 3z, and then we have plus cosine of z over 2, 0 to pi over 2, and then from here we can just evaluate this and we would get 2/3 as our final answer. And I have that on my notes as well. Perfect. Example 3, write an iterated integral for this function f of x, y, z, bounded by this region S in the first octant, bounded by the surface z equals 9 minus x squared minus y squared and the coordinate planes. Okay, before we even start off, let's just get some information down. So the first octant, we know that means that it's going to be x is greater than or equal to 0, y is greater than or equal to 0, z is greater than or equal to 0, right? Bounded by the surface and the coordinate planes. If you want to try this problem on your own, feel free to do so. But if you want to stick around and see how I would actually organize this integral, feel free to stick around with this. Let's get right to Desmos. Okay, so now I'm on 3D Desmos, right? And this is what we have right here, right? And one thing I'd like to mention is that we can just completely ignore the coordinate planes where z is not, or x or y are not positive, right? So we can actually say, using our Desmos notation, saying that x is greater than or equal to 0. So you see how that cuts it in half? Let's see, there you go. And then y is greater than, no, sorry, y is greater than, oops. Y is, oh my gosh, what's happening? Okay, y is greater than or equal to 0. Right, and now this is our region that we have right here, right? So so normally I like to do dz, dy, dx, right? So we get this as our first region. This is like the entire volume that we're integrating with respect to, right? So our z also has to be greater than or equal to 0. So I actually forgot about that too. Let's just add that. Z is greater than or equal to 0 right here. And then what we can do now is have this entire area right here. So now we can say that we know that the minimum value for our dz is going to be 0. And the reason why I chose dz first is because we have this paraboloid in terms of z, right? So actually, in our earlier example, we had it, the triple integral writing from dz as a function of phi of x and y, right? This is actually what we have perfectly right here. Our minimum value is going to be 0, but our maximum value upon any point on the curve is 9 minus x squared minus y squared, right? So that's how we know that's our dz, right? Our dy, we know, is anything along this curve right here, along this blue curve actually, because we're setting z equal to 0 for our minimum. Now we just have it in terms of x and y, right? Because in essence, actually, what we're saying is that our z can vary along anything, right? If our z was technically 9, what we can say now is that x squared plus y squared equals 0. And that actually makes sense at the top, because look right here. At the top, the radius of this would be 0, right? So we know that also. And then we can say that if it's in the first octant, we know that our bounds is always going to be from 0 to what? 0 to the max, right? And in this case, we have this right here, and we're going to get 9 minus x squared minus y squared. X squared, it's going to become x squared plus y squared equals 9. That's a quarter circle, and we can rearrange this to be y equals the square root of 9 minus x squared, right? And that's what we have right here. That green area represents the same thing. And then for our dx, we know that's in the first quadrant, so that first octant, right? Or in this case, it's the first quadrant, just we're looking at an xy lesion or a cut of this, right? And we can see that it's going to be x is greater than or equal to 0 to x equals 3. The max can be 3, right? And that is how we can define our bounds for this triple integral right here, right? So we went from the z because it was a function of z in terms of x and y. And then we varied the z from 0 to 9. We set it at its max, basically, right? At 9, it would be 0. And at z, at any point on z, it would vary, right? So then it would just become essentially a quarter circle on that bound for your y. And you could also do that for the x too. It doesn't matter. You would still get the same result, right? But I'm just doing dz, dy, dx. That's familiar to me, and that's the process that often would work out in these types of problems, or the way these problems are set up, right? Now let's actually set up the integral like this. So we have this right here, and we have f of x, y is z, dz, dy, dx in terms of this. We get 0, 9 minus x squared minus y squared, 0, 9 minus square root of 9 minus x squared, and then 0 to 3 for our variables. And that is our final answer for this triple integral right here. Perfect. In example 4, we have finding the volume of the solid in the first octant bounded by the hyperbolic cylinder y squared minus 64z squared equals 4, and the plane y equals x and y equals 4. Again, if you want to try this on your own, feel free to pause the video. I'd recommend using Desmos or some other graphing device to figure out your bounds. And let's jump right into it. One thing I would also mention too is that if you're not given a function or whatever for solving the volume, you would use one like you may have used to solve for the area of some area of a double integral, right? So if a double integral is just like the height's 1, right? Essentially, the z is 1 basically for your equation, right? That's how you get the area of it, right? In this case, we're doing that for the volume as well. That's our density. Our density is 1. And that also works out in the equation too. If your density is equal to 1, mass over volume, 1, your mass equals your volume, it just cancels out, right? So you can just say that your volume equals your mass, which we just said. Kind of redundant, we get the idea, right? Now, I'm going to go to dz, dy, dx. That's like a familiar thing that I'm doing. And let's jump right into it. So let's isolate for our z. So we're gonna get 4 minus y squared equals 64z squared. Divide that by 64. That cancels. And then we get z squared equals 4 minus y squared all over 64. And then we take this square root of everything. We get z equals plus minus 4 minus y squared all over 8. That's our z. And then we know some of our other bounds. We know that in this case, y has to necessarily be bounded between, let's just say this 2 is less than or equal to y less than or equal to 4, right? Because we know that we can't have a negative in this part of the equation right here, right? That's just not going to be practical for us to get an answer, right? And then we know that if it's in the first octant, we know that this has to be true as well. X is greater than or equal to 0. Y is greater than or equal to 0. Z is greater than or equal to 0, right? And we know that. And in this case, we can actually go to Desmos real quick. And now we can see when we have all these intersections right here, we see where our function would start and end, right? So if we even just get rid of these two right here and we just focus on the red and the blue, our blue is the y equals x, right? Essentially, our minimum for our x is actually going to be 0 because it's in the first octant, right? Again, that's another thing that we've been covering. If it's in the first octant, then your minimum can't always be 0. Don't ever forget that. If it's in another octant, you have to be conscious of the minimums then, right? Or the minimum would still be 0, but you have to be conscious of whether it be negative for your square root, for example, right? Because if this is like the second octant, your x would be negative, and you would be conscious of that. Maybe not for this example, but for other examples, right? Suffice to say, we have our bounds now. Our bounds is going to be from 0 to the square root of y squared minus 4 divided by 8 for our z, right? Because we isolated for z. Our x, because we have x, because we have to convert from y to x in this case, we're going to have our dy, or no, not our dy, our dx be from 0 to y, and then our y vary from 2 to 4. And now let's start to integrate this whole function, right? So remember what we said earlier, that if we have it be the volume of a triple integral, that means our density is going to be 1, right? So that's going to be something we have to always keep in mind when we're doing these problems. Even if it's a double integral, if you're solving for the area, the function inside is going to be 1, right? Because z equals 1, right? That's going to be your height, right? And then technically your volume is your area, your hypervolume is your volume. It's the same result ultimately, right? But just to make sure that we know that, this should be from 2 to 4. And you want to be conscious of something. I haven't said this explicitly throughout the video, but all my answers have been showing this, that your first function, for example, when you're integrating, can be a multivariable function of x and y, right? In this case, if it was dz, but if it was dy, it would be x or z, right? Then your second most inner function, your middle function, your middle bound, right, dy, can be in terms of x, right? If it was dz, it can be in terms of y or x, depending on what was your inside function, and so on and so forth. However, your dx, or your dy or dz, your outermost integral is always going to have a constant attached to it for both bounds. That is a non-negotiable in these types of problems. It would be like having a z. It would be like having a z here, leading to a fundamental to the different result, because that's not really possible in these triple integrals, right? Because you're integrating with respect to z here. How can you integrate all the way over here? It's not feasible, right? Anyways, let's get back to our actual integration process. I dropped off a little bit of the 4 there by accidentally pressing the undo button. The world keeps on spinning though, so we're all good. And now let's just jump into the integration. The integration isn't that bad, it's just figuring out your bounds. And the more you do these practice problems, it shouldn't be too terrible. So we have z evaluated from this to this. And you have it be this. Right, and then I'm going to move this over. Actually, let's just keep it, and then I'm actually going to copy. I'm going to paste it over here. Perfect. Now we have our double integral right here. We have 0 to y, 2 to 4, d. I'm actually going over to my space now. Let's write this down real quick and let's move it elsewhere. Right, let's chop it down over here. Now we can integrate with respect to x here. We will get x times this quantity divided by 8 from 0 to y, right? And we get y times the square root of y minus 4, y squared minus 4 divided by 8. And then we have our final integral we can work with. 0, not 0, it's going to be from 2 to 4 of y times y squared minus 4 divided by 8 dy. And then we're going to do a u sub for this because I think it's way easier than not doing a u sub. I'll write that in white. Actually, I can write it in blue because I'm feeling fancy today. U equals y squared minus 4 2u, not 2u, du equals 2y dy. Oh shoot, forgot the dy right there, silly me. And then we can replace our bounds now, which is going to be 0 and 12. I do that mentally at this point, so apologies for that if you may have been lost. Let's bring out the 1/8 here. We have y times this whole quantity, and then we do divided by 2y. Actually, no, I'm sorry, it'd be 2 be du over 2y like this. That cancels. And then you get 1 over 16. 0 to 12 of u to the 1/2. And then you get u to the 3/2 over 3/2 evaluated from 0 to 12. And then you would get 2/3 times the 1 over 16. Don't forget that constant out front. That's going to be turning into 1 over 24. Yeah, 1 over 24 times this whole quantity, root 12. I'm going to write the square root first. Actually, let's write it as 2 root 3 cubed. It's going to be 8 times 3 root 3. That's 24 root 3. So it's going to be 24 root 3 over 24. Where did I go? Oh my gosh, my iPad's glitching now. Perfect timing. And then we get root 3 as our final answer. Perfect. And for example 5, find the volume of the tetrahedron with vertices at the origin, 0, 0, 3, 0, 4, 0, and 2, 0, 0. If you want to solve for the tetrahedron on your own to solve for this, feel free to do so. I have a shortcut if you want to see that as well. And let's get right into it. So the shortcut that I like to use, honestly, is I see that we have going from 3, 4, and 2. I like to find the least common multiple of that, right? So 3, 4, and 2, it would be 12, right? So it would be 12 as our answer. And then we have to go for our x first. So our x is going to, how much we have to get from 12 from 2, right? So 12 divided by 2 is 6x, right? So if I plug in the origin 0, we know that's fine. And then if we know we have to go 2, so it's going to be 6 times that, right? And then we can do plus 3y plus 4z. Another way you could have done this also, and this probably should have been the way your Calc 3 professor should have taught this, is if you have these points, I'm going to label them like this: 1, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4. And if you have 2, 0, 0, I'm going to call this my x, y. 1, 2, 3. Sorry, that should be out there. You get something like this, right? You can then just extrapolate that from here. I did the shortcut way, but it doesn't really matter. You got to your tetrahedron, right? And again, you want the volume, so your function is actually just going to be a double integral instead of a triple integral, right? But you can also just write it as 1 dz dy dx, right? Or dx dy dz, or any other way you want to write it, because in this case, it doesn't really matter. But let's just jump right into it. So let's solve for z real quick. We're going to get 4z equals 12 minus 6x minus 3y all over 4. So we get that. And then let's solve for setting z equal to 0. Z equals 0, we get that. We get 6x plus 3y equals 12. So we get 12 minus 6x equals 3y. Divided that by 3, we get that. And then our bounds from our x are going to be from 0 to 2. Perfect. So now we can just plug and chug everything in, 0 to 2. And then we have 0 to 4 minus 2x. Yeah, 4 minus 2x. And then we have our dz just be that whole cluster of an equation. 6x minus 3y over 4 dz dy dx. And then we can start our integration process. So we got that z's from this to this. We got this as our resultant. I'm not going to write out the 0 because I guess we can, because I just said it. Doesn't really matter for our result. It's all good though. We have our double integral 0 to 2, 0 to 4 minus 2x for our new function. And again, I'm going kind of fast. Apologies for that, but this is another mechanical process-driven problem. It's not too difficult conceptually. If we can identify that we have like a volume of a 3D shape that we're trying to solve for, we can just rewrite it as a double integral, right? And have our z be technically our density function, right? That's another trick as well, right? Or your area density or your linear density, right? So on and so forth for single integrals. From here, we would integrate this, where we got 12 over 4 y minus 6xy over 4 minus 3y squared over 8 evaluated from this to this. And this is a lot of algebra that I wrote down on my paper, and I will post these notes eventually, but I am not going to be showing in this video because my calculus skills at this point in my life are better than my algebra skills, and I have the resultant right here. Perfect. Let's copy and paste this again, saving me about 5 seconds, but making the viewing process hopefully a little bit more manageable on your end. And we get 6x minus 3x squared. And then reverse power rule, the 3 cancels out, so we plus 1 half x cubed, 0 to 2. So we have, what's this? Everything's going to go to 0 because there's no constant, right? Yeah, or just all polynomials. Minus 3 times 2 squared, 12 minus 12, plus 1 half 2 cubed, 8 times 1 half is 4, so 12 minus 12 plus 4 equals 4. That is our final answer for this problem, and that is the final problem in this section. Thank you so much for watching, and I hope you guys have a fantastic day.